Okay, hello everyone. This presentation is called Better Java Builds with a Mill Build Tool. So just about myself, I'm from Singapore. I've been an open source developer since 2012, have a number of open source projects, mostly JVM related, some in the Scala programming language. Worked at Dropbox, Databricks, authored the book Hands-on Scala Programming. So this talk will cover what is Mill. Mill's a new build tool. Why would you be interested in Mill? Why should you care about this new thing? And how does Mill work? Like, how does Mill do what it does? So first, what is Mill? So Mill's an open source JVM build tool. It's not a new tool, but it previously targeted mostly Scala projects. And more recently, earlier this year, it's been kind of expanding to target adjacent Java and Kotlin projects. If you're not aware, Scala is another JVM language, so the syntax is a bit different. There's no semicolons, but all the assembly, class files, jars, all that's exactly the same. So although previously worked for Scala, it actually works pretty well for Java projects, including things like Spring Boot, Micronaut, and all that kind of thing. Mostly does the same thing as Maven or Gradle. You know what your build tools do. But aims, one, it's easier to extend and easier to use. And two, it's currently about 5 to 10x faster than Maven on my benchmarks, and 2 to 4x faster than Gradle for equivalent local builds. And I'll show them off later. The documentation's on millbuild.org, so for those of you who have your laptops open, you can go check it out. A lot more detail there than I can go over in this 45-minute talk. So mill build looks something like this. So on the left, you have this build.mill file, this equivalent to your build.gradle or build.sbt or pom.xml, build.bazel, etc. You have some import boilerplate. You have an object that extends Java module. This is Scala syntax, but I can probably guess what it does, and you'll guess correctly. It looks just like Groovy or Kotlin or Java without semicolons. Have dependencies on argparse4j and timeleaf. It looks kind of like Gradle. And I have a test module which extends Java test and some JUnit configs. So from this, I can compile it. I can foo.run, pass in arguments. I can foo.test, create the assembly, run the assembly later, all your standard build tool stuff. So let me just show it to you now. So here is my, is this the right one? Yep. So here's the same module I had just now, Java module. Here's some small Java implementation just for sake of the demo. I'm using timeleaf, I'm using argparse4j. I have a small test suite that just asserts some hello world stuff to show it off. And I can run mill foo.compile. So it's already been compiled. I compiled earlier, so I can foo.run text like hello. I can run foo.test. Foo.assembly, can show off the assembly, then it tells me where it is. I can run the assembly directly. They ask me to put it, so hello world, or I could run the assembly using java-jar, which is what you may be more used to. And it does the same thing, it prints out this, and it's using timeleaf, so I can try and put in some sketchy script tags in here, and it should get escaped correctly using the timeleaf templating library. So nothing surprising here. All of this is kind of boring build tool stuff. So the question next would be, why mill? Why should I bother with this? It's the same but different, but is it actually the same? So I guess the basic reason why I worked on mill is that JVM build tools have a reputation for being both slow and also confusing, which is also a bit weird because Java has a compiler that's really fast, and Java language is really fast. And Java is also really easy to learn, easier to learn than C++, easier to learn than JavaScript, TypeScript. So if the language and compiler and platform are also fast and easy, why are build tools so slow and hard? So that's what Mill is trying to solve. So in terms of performance, depending on what build you're looking at, I was seeing 2 to 10x speedups in local builds. Ease of use, ID, support, and tools to look at what your build is doing is much better than Maven or Gradle, despite being a much less popular tool. And in terms of extensibility, you can directly write code to do what you want, or just grab things off Maven Central without having to find a foo plugin to do foo in your build or a bar plugin to do bar in your build. You just take foo directly and use it, and you already know how to use things from Maven Central because you're Java programmers. So first, let's talk about performance. So just the example I showed you earlier is kind of a hello world example, which is boring, and it's always going to be fast no matter what build tool you use. So to do something more realistic, I went and got the Netty code base. So who here has used Netty? Netty is the asynchronous web application server framework. You can have a lot of backend high-performance async stuff is written using Netty. It's like async Jetty. And it's about 500,000 lines of code, 3K source files, 50 sub-projects. Netty already has existing Maven build, and I just manually ported it over to use Mill. It's not that big a project. It's big, but it's not huge. It took about a day or two. And although the port is not 100% feature complete, like it doesn't build correctly on all 6 operating systems and CPU architectures, it's complete enough to do like a comparative analysis to see how these 2 build tools compare with each other. And all the tests pass on both, so it's not just compiling the code and throwing it. We actually ran all the test suite. Mill does support running JUnit tests, and they all pass. So it's a quite comparable build setup. And these are numbers I got from Netty compiled using Maven and Netty compiled using Mill. So you see on Maven, sequential clean compile takes about 2 minutes plus. Mill, it takes about 20 seconds. The other numbers are kind of comparable. The incremental numbers are even more stark because Maven doesn't do a really good job at incrementally. I change a print line. It still asks me to recompile the whole module pretty wastefully. And Mill does a good job at that. So let's look at, I don't have time to go into all of these benchmarks, but let's look at 2 of them. First, parallel clean compile all. So on Maven, this took 1 minute, 16 seconds. Mill took about 10 seconds. These are 2 commands I use. So Maven clean install, I'm using this because Maven compile doesn't always work, and if you don't clean, it also doesn't work. And on the Netty code base in particular, you try to use Maven clean compile, it doesn't work. So I had to use Maven clean install. I disabled the tests. I disabled the linters for now because for Mill, the linters are separate commands. So just to make them apples to apples comparison, you're only compiling code and only compiling all the Java code, but not running tests, not running linters, and so on. So we can see this in action now. So I have my terminal here. If I go back down to Netty and I run this, so Maven parallelism is opt-in and you pass in -T10. That's just the way Maven is. For Mill, it's automatic. And it's compiling a lot of Java source files, as you can see, but it's also doing a lot of other things. Like it's downloading stuff from Maven Central, even though I have everything cached already. It's building a bunch of jars. I didn't ask it to build, I don't need it to build jars. And it's comparing jars. It seems to take quite a while sometimes. And in the end, it should take about 1 minute, 16 seconds. So you do the math, right? So you have 500,000 lines of code, 500K. It takes about 75 seconds to compile. So it's compiling at about 6,000 lines a second, which is honestly very slow. The Java compiler, you kind of actually benchmark it, compiles at about 20 to 40,000 lines a second. So if Maven takes 1 minute, 16 seconds to compile 500K lines, that's way slower than it should be. And it's not Java's fault. Java's fast, but the build tool and all the associated stuff around it, all the jarring and unjarring and stuff, that's what's making it slow. And remember, I have 10 cores on this MacBook Pro, so it should be very parallel and very fast. But I've talked a while and it's still running. So you can see, I don't know how many of you spend a lot of your day doing this, but at least in my previous jobs and stuff, we spend a lot of time waiting for compiles. And 1 minute, 16 seconds finishes right about now. Okay, today it took 1 minute, 20, more or less there. So let's look at Mill. Mill, as I said earlier, the parallelisms by default, there's a flag to turn it off. The test suites are the opposite, there's a flag to turn them on. So, but this does basically the same thing and compiles all the Java code. And let's paste this in. So clean, and the compile, and it just starts churning away. It actually compiles all the same source files. I've actually looked at the logs, regex the logs and find how many source files each one compiles in the logs and added them up, and they do compile the same set of source files in the same modules, so it's not like I'm doing less work here. But now it took 14 seconds. Mill's a JVM program, so you run it again. It's like Gradle. There's a background daemon that warms up over time. And this one takes 9.2 seconds. So this is basically the same numbers as we saw in the benchmark. So what's happening here? What's happening is that Maven is doing a lot of things that it probably doesn't need to do. So if you run Maven compiler, it is a lot faster than Maven install. But if you run Maven compiler on a large multi-module project like Netty, it often just doesn't work because of a number of ways the Maven setup makes it hard to get it correct. So Netty build is not correct for compiling everything just by compile, and you need to run clean install, which I'm sure many of you have experienced at various Maven projects if you've used Maven. For Mill, not only can you just run mill compile, it's actually really fast and makes use of all your cores and just churns away and gives you output in literally, in this case, about 8x faster than Maven does. So that's interesting. The next benchmark I looked at is incremental compile. Add a change to a single file in the common module in this case, and use Maven to only compile that module. Again, skip test, skip, blah. So this compiles both main and test code, and I did the same for mill. So mill, I asked it to compile test, and it compiles main automatically because the test depends on main. So let's do this in the terminal. So I'm just going to paste this here and paste this here. And it's going to take a lot shorter than it does the first time, but it still is going to compile a lot of, do a lot of stuff, and takes substantial amount of time. You can stand here awkwardly while we look at the logs, just like we do at work all day. And here we are done. Okay, this time it took about 21 seconds, more or less what we saw on the benchmark. How about for mill? So for mill, I paste this in, compile one Java source file, took 1.5 seconds. Okay, let's run that again. Compile one Java source file, took 0.7 seconds. And really, how long should it take to compile one Java source file? Java source files compile at 20,000 lines a second. The Java source file is probably going to be on the order of like 1,000 lines. It's going to be like, what, 0.05 seconds? So even 0.6 seconds is a lot of overhead, but it's a lot less overhead than the 20 seconds we saw Maven doing to do basically nothing. Like in this case, I'm literally adding a new line to the end of the file. There's no change to output bytecode, input AST or anything, but Maven's not quite smart enough to recognize that. Whereas the incremental compile that Mill uses called Zinc can do it somewhat more intelligently.
Can I ask a question?
Yeah.
Maven's comparing those jar files, looks like the snapshot to the previous version.
Yeah.
Is that a plugin that Maven has built in by default that Mill isn't running? Or?
I'm not sure actually. That's part of the Netty build. So it's probably not ideally configured, but neither is the Mill build. These are all kind of just best effort. So I can't really say the optimal Maven build, but this is a real Maven build I just grabbed off GitHub. You go to Netty on GitHub, this is what you'll see. And it's probably what many of your own builds look like. Yeah. So that's Mill versus Maven. The other thing that we benchmarked was, so Mill versus Maven, these are numbers, a lot faster in many common workflows, at least for the benchmark we did. Your mileage will vary. The other thing we did was compare Mill versus Gradle. So Netty does not have a Gradle build, so I went and found another open source project that does have a Gradle build, and I found Mockito. So all of you have used Mockito probably. You've used the JUnit, used for unit testing. Smaller, about 100K lines of code, 1,000 files, 20 sub-projects. And again, took the existing Gradle build, just manually, a bit tediously ported it to Mill, just to compare for comparison purposes, but complete enough that all the tests pass, at least on my MacBook Pro and in GitHub Actions in CI. So for Gradle, the comparison is not as stark as with Maven. You can see that for the clean compiles, Mill is about 3 to 4x faster. For the incremental compiles, Gradle is much smarter than Maven and is able to kind of avoid doing a lot of the work, but still Mill has less overhead than Gradle does by about 2x to 3x. So again, let's focus on two of these benchmarks. The parallel clean compile all benchmark. This is the command I use. Again, I want the classes only, no build cache, don't run linter, that's why I didn't use Gradle build. I ran clean beforehand. So first, let's go over here to our Mockito checkout. And let's take a look at it, right? So we can look for the Java files. We can count them, about 1,000 of them. We can use exile to count each one and sum them up, about 100K lines. So this is like the Mockito code base, not small, not big, kind of medium size. So let's time building it using Gradle. So this should take on the order of like 10, 20 seconds. You see, Gradle does parallelize by default like Mill does, and it's running. This last module is a bit large, so it takes a bit longer to compile, and we should be finished in a moment. And here we are, about 19 seconds. Yeah, if I run it a few more times, it'll come down to about 12 seconds because JVM has to warm up. I won't bore you. So for Mill, I'm going to run this here. And you can actually see it's compiling the same set of modules. Like both Gradle and Mill have this nice parallel, what's it doing at any point in time. Both of them got stuck at compile, then did a bunch of other stuff, then got stuck at test compile, and it takes a while to finish test compile. And it's actually the same set of modules, but Mill finishes, in this case, for 8 seconds. So if I run it a few more times, it'll get faster. Let's try that. So run it again. Okay, down to 5 seconds. Run it again to warm up. Yeah, down to like 4-point-something seconds. So this is more or less on an order of magnitude that we saw on the benchmark. The other example we wanted to look at was incremental clean compiles. Sorry, incremental compiles for a single module. Again, I add a new line to a single module and then run compile. So Gradle is smarter than Maven. It actually finishes pretty quickly by realizing it doesn't need to do much. 1+ seconds of overhead. And Mill is just the same but faster. So there's 2 seconds overhead, and you run once or twice down, so at 0.5, 0.6 seconds of overhead. Again, it kind of logs out. You know it compiled only one file, that's why it's so fast. And it knew it only needed to compile one file because it compiled it before I knew that this file didn't change much, so it just recompiled that one. So here's, again, the statistics for Maven versus Gradle. Sorry, Mill versus Gradle. Not as stark a difference as Mill versus Maven, but still quite significant, right? Like you have 3x faster local development, or whether it's incremental development or clean compiles. That is non-trivial improvement in your day-to-day life. So that's the performance angle. So you get faster builds, means less time waiting for builds, means more time doing the actual fun stuff. And the next thing we're going to look at is ease of use. So Mill has full ID supported IntelliJ VS Code and good tools to look at what your build is doing. And I'm going to look at them now. So one of these tools is the Chrome profile. So this is most useful when you're wondering why is my build taking the time it's taking. And let me show it to you now. So to get a good profile, I'm going to go and do a clean build, because if you do incremental build, it's not doing anything, so that's not interesting. You do a clean build, it's going to do a lot, and you can see it doing a lot. So if I look at out folder, which is equivalent of the target folder, there's a bunch of metadata JSON files you can ignore. And then there's a Chrome profile.json. So what's a Chrome profile.json? Chrome profile.json is a JSON file that happens to be compatible with your Chrome browser's built-in performance profiling UI. So I can open this. Let me open up a Chrome to put here. Where's my mill-chrome profile.json? So Chrome has this built-in performance tracing UI. Who knows about this? Who here uses Chrome? So if you use Chrome, this is a thing, and it's actually very handy. Like, it's just built in for all your computers for free. And I can just drag in this, my Chrome profile, and see, hey, this is what my build is taking on each of the 10 threads I was using on my 10-core laptop. That's really handy. I can see that you kind of saw in the terminal that compile was taking a while, and then it finished, and a bunch of other stuff happened, and test compile took a while. But we can see it very much more clearly here and say, okay, well, test compile actually did take exactly 2.524 seconds to complete. And if I want to optimize this build, well, these are the things I can look at optimizing. Maybe test compile can be broken up into separate modules, smaller modules that compile in parallel. Or maybe some of these can be moved so they don't depend on compile. Maybe only depend on some subset of like utility functions or helper functions. So that's one thing that Mill does. And we can go to the Netty codebase and see what it looks like there. So mill clean time mill compile. And the underscore is just a wildcard. It just means like it's like double star, find everything recursively, all the compiles that you can compile. So let's run this. It should be almost done. So I'm just going to open out. Here's my Chrome profile with all the metadata output. Oops, not the launcher, the Chrome profile. Yeah, and here is my Netty performance profile of my Netty build. All the small stuff up front, a bunch of small helper, resolving IV dependencies. Then it took a while for common to compile. After common to compile, a few other things kicked off. Buffer, transport, codec, and only after codec finished could a bunch of these other tasks compile, and so on. So, and microbench was at the end that took the longest. So this really helps you figure out what is worth looking at and what's not worth looking at if you want to optimize your build. Like you can kind of guess by looking at the terminal output, seeing what's running, but this gives you exact numbers and helps you really visualize what's going on. And it basically comes for free. You don't need to go pay Gradle Enterprise. You get this. Everyone who has Chrome browser gets it already on your computer. The other thing that Mill gives you is the ability to visualize module structures and other structures in your build. So if I go back to Netty, I can say Mill visualize wildcard compile, and it will look at the graph because your modules form a graph and your tasks and everything form a graph. So it looks at the graph and gives you the graph. In this case, you have different formats. You have the dot file, you have the JSON, PNG, SVG text. Let's look at SVG. And this kind of shows you the module. This shows you the module dependency graph of your Maven, of your Netty Mill build. And it's the same graph as your Maven or Gradle builds. They all have this graph internally. But Mill just gives it to you very easily, so you can just look at it and see what on earth is going on. And we can see what we saw in the profile, right? Like, what did we see here? We saw common compile took a while, then buffer, then transport, then codec, then some others, then handler, then other stuff after. Well, in my graph here, I can see common compile is required by buffer, required by transport test, and after transport test, all this other stuff compiles, which is probably what we are going to see on the right, somewhere around here. So this is it's the same data, maybe just another view of the same data, and really helps you understand what's going on and gives you more ideas of what you can do. So for example, right, all this stuff here depends on transport test.compile. Transport test.compile might take a while. Does it really need to depend on the whole test module, or can it depend on some helper like test kit or test utils? If you can, that will let you move all that stuff earlier on and really make better use of your CPUs than what we are doing here, where here we can see early on we make great use of filling up all the CPU cores, but later on we're kind of just using 2 or 3 cores at a time as if I'm on like a Pentium 4. So that's Mill visualize. The next thing I want to look at is ID support. So Mill's not a terribly popular project. It's a smaller project, much nicher than Maven or Gradle, but it already has pretty good ID support in IntelliJ and VS Code, and we can take a look now. So I'm just going to do side by side. Here is, okay, on the left side is the Mill build config for Mockito. On the right side is the Mill build config the Gradle build config for Mockito. They contain more or less the same things. Like you see all this stuff here, it does appear all here. Mill does not magically make your build config disappear. You still need your Java options. You still need to configure your boot class path correctly and all that stuff. That's all the things I had to preserve while porting the build from Gradle to Mill. So what Mill does do is it helps manage this complexity much more easily. For example, let's say you don't know what JVM args is, right? Okay, it looks like IntelliJ kind of knows. You can jump to definition. You get decompiled bytecode. And not only do you get decompiled bytecode, you can't jump anywhere else from here. You're stuck. You can't search for it. What does get JVM args end up going? You don't know. You hit the wall when you're inspecting your build. And you can look at elsewhere, right? How about options.compiler.args? Well, options goes to get options. Get options doesn't really tell me what get options does. It tells me I'm using get options, but what does get options do in Gradle? You don't know. What does get options.compiler.args do? Get compiler.args? It tells me I'm using it, which I already knew, but it doesn't tell me what it does in Gradle. In contrast, we can look at what happens in Mill, right? So Mill at surface also has compiler. It also has jump to definition. You can jump here and say, okay, this is used in a few places. It does have the type annotation. You can see here, IntelliJ is filling in, telling me there's a sequence of strings because I left it out. You may not be super familiar with the Scala syntax, but you can probably guess what it does. It looks like Groovy, Kotlin, somewhat like Java. You know what it does. But if I jump here, I can see, well, IntelliJ knows that fork args is an override of the equivalent task in Java module. And it knows that Java module is an override of the task in run module. And in run module, I can see fork args ends up being used by runner here. That's kind of nice. I can see runner ends up being used by run background task or run fork task. And run fork task, if I look at it, ends up being used by the run method. So this is, you might not be familiar with the syntax here, but basically what we are doing is the IntelliJ IDE is able to jump around my task build graph exactly the same way you jump around your method call graph in any application code. So none of the stuff I'm doing here is magic, right? Like you already are used to seeing overrides. You're already used to jumping to the traits and seeing where they come from, or jumping to superclasses and interfaces, seeing where they come from, and jumping, oh, what does this have? Well, Maven module is a Java module with these things. What's Java module? I can jump to this. I can jump to this. Of course, you can jump around your code and see what it's doing. So that's not rocket science, but that's something that Mill kind of allows you to do that most other build tools cannot. Mill takes the IDE experience of your application code and ports it to your build code, so you can really just enjoy and explore your build code without having to Google what's going on. Like I could Google what forcx does. Google will find the documentation to tell me. But I can also just jump to definition and see like, okay, well, here's the override, find the usages, and just trace through the IDE just like you would in an application. So that's the IDE support demo, and hopefully you find it interesting. And that's it for ease of use. So you get introspection tools like profiles, graph visualizations, all your IDE, jump around. All this works in VS Code as well if you use VS Code. And it's a great ease of use experience. The last thing we're going to look at is extensibility. So most build tools require extensions to be published as plugins, and you want to use you need a full plugin. You want to use ThymeLeaf in your build, you need a ThymeLeaf Maven plugin or ThymeLeaf Gradle plugin. You don't have a ThymeLeaf Maven plugin, you go start learning about mojos and a bunch of other stuff you probably don't want to learn about in order to get this integrated into your build. And as a result, people often don't do stuff in the build when maybe they should be, right? Like maybe you should be pre-computing your templates in your build so you don't need to spend so much time at runtime or so much time at application initialization to initialize your stuff before your program starts running. But because people are uncomfortable adding stuff to your their builds in Maven or Gradle, it generally doesn't happen. Your applications get slower or they start up slower as all that stuff gets pushed to application start time. Because at least that's Java and you know how to write Java, whereas your build is in like Gradle, Maven, stuff that you don't actually know how to write. Mill is different and lets you write code and import any library from Maven Central to use without needing to have a specialized plugin. And we'll see that now. So here's an example Mill build. For now, it's like the 0 build. Like there's nothing here. There's one object full Java module. There's all the default config, default class file layout, default source file layout, all that. You can compile it. It works. If I want to add a custom task in Mill, it's as simple as saying def something equals a task with some curly brackets, and then put what the task does inside. In this case, I'm calling this all source files. Task that is inherited from Java module. I map it to read the lines, get the size, compute the sum. You might not be familiar with this library and syntax, but you can probably guess what it does. And then I can call mill show full line count in my terminal and show what the value of the task is to help debug it, which is also very handy. Like, what's this task doing? Who's misbehaving? Well, I can ask, what are you doing? What are you returning? What are you returning? What are you returning? And eventually, you'll find who's misbehaving. After I define the line count task, I can define the resource. I can override my resource task and say, well, resources is now not the previous resources, but it's the super resources plus the current folder, the task like destination folder, and I'm going to write the line count txt into the task destination folder. So, and then when I run use foo.run, it can then pick this up at runtime. So let me just show it to you right now. Where's my demo? This one, okay. So here's the build we saw on the slide earlier. Here is my example application code, just prints out the line count, nothing special for now. And I can say, let's go down to that folder, /mill show foo.line count. So first time takes a bit slow to warm up, second time it's fast. I can show the resources. You can see that, okay, now the resources have two entries. It's both the resources folder as well as this like generated resources.destination folder, which is what this task.destination means. And I can do foo.run. I don't need the show, I just need foo.run. It prints out the line count 17, that's what we saw in the Java code. I can inspect foo.line count. I can see that, okay, the foo.line count defined on build mill line 6 over here has this just Java doc from here, and it inputs is this all source files, which is what we saw here. I can do the same for foo.resources. And generally, what this does is it makes your experience of adding stuff to build very easy. Like I just added a custom task, custom resource handler, complete with documentation. Everything works in the terminal as well. I can see everything in the terminal. And I did it in like 5 lines of code, all of which is statically typed, so you make a typo here, it'll screw up. You can ask for documentation for any of these things, it works. You don't know what it's called, you just start typing and IntelliJ will fill it out for you. You know that experience. It works the same way as it would in any large Java application or small Java application, and now it works the same way in your build. So let's say I didn't want just to add like a line count txt file. That's boring. Let's say I wanted to pull in some third-party resources. Earlier on, I mentioned maybe you want to render some HTML templates at compile time, at build time using Timeleaf. Well, over here is an example of just doing just that. And I'm just going to do it live for you so you can see. So over here, I'm just going to copy-paste the imports. So where is my custom? So you see, okay, Mill doesn't know about these things because Mill does not come bundled with the HTML templating engine, of course not. But because I have this magic import, the $iv here, I can put this here, reload the build in my IDE, and Mill will then be able to understand all these imports. I can make this go away. Understand all these imports. And now I can immediately say, instead of line count, I want HTML, rendered HTML. Instead of using like all source files and reading the lines, I can say, okay, I want context is a new context. I can say context dot set variable, not get variable, set variable. And I can say, okay, heading is hello. Maybe I add some like sketchy stuff to make sure it works. Then I can say new template engine dot process. And then I'm just going to copy paste the template syntax, so it's a bit finicky, lots of quotes and things. Dot process. This is just that standard Timeleaf, and you pass in the context. And then you see that I've renamed it. This guy is telling me, okay, I need to rename that to fine. Instead of line count txt, let's call it rendered.html. And instead of over here in the application code, I'm just going to call it rendered.html. And then like rendered HTML is the snippet. So now I can run this. You see, it has to recompile and recompile the build file. It's recompiled the application code because I changed both of them. And now I'm seeing my rendered HTML that's generated at build time using a third-party library from Maven Central that you probably may already be familiar with because you use it in production, and stored as a resource for me to use at runtime. And I can just do this without any sort of Timeleaf, Mill integration plugin thing. I have Mill, I grab Timeleaf from Maven Central, I can start using it. If I want to use Guava, I want to use Apache Commons, I want to use this or that. Maven Central has a lot of things, and it's very nice to be able to take any of it in your build and write direct code with like full autocomplete, full IntelliJ support and all that, full type checking in order to get what you want done. And again, like this code is in Scala. You might not be familiar with Scala, but you can kind of guess what it does. It's just like Java without semicolons. It looks fine. So that's the extensibility story, right? Let's go back here. So the promise of this is you don't need there are plugins, but you don't need plugins for every small thing. Just write the code you need, import libraries you need, and get the work you need done. And this performance, ease of use, and extensibility is why you may be interested in Mill. So the last part I'm going to just talk about briefly is how does Mill work internally? So far, I've just been showing it from a user perspective, like what you can do this, you can do that, you can do that. What's going on inside? So internally, Mill, it takes these objects, which are just Scala objects or JVM singleton objects, and these objects inherit methods from the superclasses or default methods from the interfaces. And these methods form a call graph, right? I call you call you, and the data comes backwards to in the end, the first person who called someone. And so on the top right is a simplified version of this call graph where there is an assembly method, there is a resources method, there's a class path method, a compile method, and a source method. They just call each other and pass things down, and they return the values back up. And the Mill call graph looks exactly like the build graph, which is why it's so easy to navigate around in IntelliJ, because IntelliJ does no build graphs, but IntelliJ does no call graphs. So when I start adding methods and overriding things, like I add line count calls all source files, I add override resources calls line count. I'm changing the call graph in this way, But because I'm using normal methods to do it, you guys already know how this works, right? Like, you guys already know that when I override resources, assembly will call the overridden version. That's how override works in Java 101. You guys already know how super works here. It's calling the previous resources before I override it. So although there's this whole graph thing and module thing and build thing, you actually don't need to know much more than you already knew learning to program in Java. You know how methods work, objects work, override, super, traits, not traits, interfaces with default implementations, superclasses, all that is exactly the same here, just a slightly different syntax, but the concepts are identical. And furthermore, if I look at, let's say I kind of add like fake stubs here to say these are sources and these are assembly that I inherited. The graph in the top right, which is the build graph, is exactly the same as the call graph you see on the left in the code. Like who's calling who and whose data is being passed to who is exactly the same as what you're seeing in the top right in the build. And that's why IntelliJ is able to find its way around mil build so easily. Once mil has this graph, mil is able to say what can be parallelized. For example, it knows that compile and class path can be run in a separate thread from line count and full resources because line count does not depend on compile and vice versa. On the other hand, assembly needs to wait for both the blue and red threads to finish before it can start because assembly depends on both of them. Mil is able to give you automatically cached things on disk. So for example, foo.linecount goes into out foo linecount.json as the metadata. In this case, like 17 we saw just now. Foo.compile goes out foo compile.json for the metadata, and out foo compile.dest, which is like a destination folder you can put your stuff in. That's what you see this task.dest here is. And if I wanted you to guess where foo.assembly goes, well, foo.assembly goes to out foo assembly.json and out foo assembly.dest, all done kind of for you and very predictably. And if you change a file, let's say you change a file in resources, that's one of the inputs to the build graph. Mil has this graph data structure. Just do a breadth-first search downstream in the graph and knows exactly what needs to rebuild, in this case resources and assembly, and what does not need to rebuild, line count, compile, or class path. So what's most interesting about this is the code on the left you see here has nothing to do with caching, parallelization, cache invalidation, lock semaphores, mutexes, all that stuff. So you don't need to care about that because mil takes care of it for you. Mil does a parallelism, does a caching, does invalidation. You just write your boring straight line direct code, and mil does all the other things, which also means that you cannot get it wrong, which is one of the reasons why mil is able to parallelize and cache things much more aggressively than tools like Maven or Gradle. At Maven and Gradle, you have to ask every plugin author to make sure you're cached and parallelized correctly. Some will get it wrong, some will get it subtly wrong and might not notice. And in the end, you get some caching, some parallelization, but won't be optimal. Whereas in mil, the plugin, the customizer of the build doesn't need to know anything. They just write code, and mil does everything for you, and you always get optimal amount of caching and parallelization given the build graph, which is very nice. So that's how mil works. This is the last slide, so I'm basically done. So what is mil? It's an open source build tool. Previously Scala, now supports Java, Kotlin. It's much faster than Maven and Android, at least the benchmarks we ran, which I think are reasonable. Not 100% precise, but good, pretty close. You have good visualization tools, good IDE support. You can directly write code or import any library from Maven to use in your build. No need to find the plugin to do exactly what you need. And internally, how mil works is that mil modules are just JVM objects. Mil tasks are just JVM methods. And from this, because your IDE already knows how objects and methods work, your IDE can help navigate this object graph, navigate this task graph, and these modules and task graph give you automatic caching and parallelization that everyone wants in their build, but no one wants to do, and so mil will do it for you. So that's it for the presentation. There's more stuff on milbuild.org. If you're interested, you can go open it up on your laptop or phone. So this is still a pretty small project compared to Maven or Gradle. There will be edge cases you'll hit, but try it out, see if you like it, report any errors. We can probably fix them if something comes up, and we'll see if we can make this good. Thank you.